Hello everybody, my name is Antonio Mastropalo and I'm from Università della Svizzera Italiana in Lugano, Switzerland, and today I'm going to present you the following work. Using deep learning to generate complete log statements. Okay, let's start. So what are log statements and in general what is logging? Well, logging is a widespread activity among developers since log statements are used to record valuable runtime information about applications. And each log statement is assigned with a log level describing the severity of the action of the behavior. And then besides the log level, we also have the log message that the developer needs to carefully pick. But why specifically developers use log statements? Well, it turns out, thanks to this study did by ordinary colleagues, that developers insert log statement to expose and register information about the internal behavior of software artifacts in a human-comprehensible fashion. And several studies have been already done showing the importance of logging in software maintenance activities ranging from software testing, software diagnosis, software monitoring, and many others. Specifically, what you and colleagues find out in this study is that developers make massive usage of log statements and they continuously evolve them in order to improve debugging activities and software maintenance activities in general. But when we think about logging activities, we should also take into consideration that such activity, it actually includes three different sub-activities from a developer point of view. Because when a developer is given with a code snippet and the developer wants to inject in the code snippet a log statement, the first thing that the developer needs to realize is where to put this log statement. After that, the developer also needs to consider a meaningful, and in this case, a very specific log level for the severity of the behavior, and also a meaningful log message that helps the developer of keeping track of the desired behavior. For this reason, several approaches have been presented supporting developer during logging activities. For example, Zhu colleagues presented a log advisor. Log advisor is an approach that can suggest developer where to add a log statement. Recently, DeepLV, that is a neural-based model, has been presented by Lee colleagues. DeepLV can automatically fix and suggest already typed log levels in Java methods. However, DeepLV can only recommend a fix concerning the log levels. And as of now, there are no approaches that can take care of these three different activities at the very same time. For this reason, we made a first step trying to overcome this limitation by presenting LACNE. LACNE is the log statement recommender tool that can help developer by supporting them in these three different logging activities. Specifically, LACNE can suggest developer where to add a log statement in Java method by picking also a meaningful log message, and on top of that, by choosing also the right verbosity. We built LACNE on top of the T5 model, and let me give you some details about the T5 model. Okay, the first thing is that the T5 model was presented by Raffaele colleagues from Google in 2019, and among several characteristics show are very interesting for the kind of task that we aim at supporting. The first one concerns the overall training pipeline, because the T5 model can be trained in two different phases. The pre-training that we can see on the top part of the figure, and then the fine-tuning on the bottom. Now, concerning the pre-training, the idea is that what we want is that the model learns which are the most recurrent pattern of the language that the model is working on. In other words, if the model is working on an English language, at the end of the pre-training, what we aim is that the model has learned which are the most recurrent pattern of the English language. Similarly, if you're working with a programming language like Java, at the end of the pre-training, we wish that the model has learned the most recurrent pattern of the Java programming language. The second part of this overall training pipeline instead is the fine-tuning. During the fine-tuning, we want to specialize the model on a specific downstream task. The second characteristic instead is the so-called multitask framework, because the T5 model can be leveraged in such a way to support several tasks at the very same time. For example, in this case, the T5 model is trained on 4 different tasks, translate English to German, call a sentence, and so on. At the very same time, the T5 model learns how to support these 4 different tasks. But why we pick the T5 model specifically? Because it has been already used in several other works supporting code-related tasks, and in several works, the authors reach new state-of-the-art results for the specific task they aim at supporting using the T5 model. Okay, and in order to give you a better overview about this work, let me also explain the approach that we came up with. So, we first start with the dataset construction that we need for training the T5 model. Now, concerning the dataset construction, we collected more than 5,000 Java repositories hosted on GitHub. Then we filtered out only those repositories having an explicit dependency towards log4j. And after this process, we ended up having more than 1.4k Java repositories. After that, we also extracted all the Java methods having no log statement whatsoever from these repositories, and later we also collect more than 153k Java methods featuring at least one log statement from these same repositories. Okay, and at this point we can dive into the experimentation that we performed. But before doing that, I also want to remind you that, as I said before, the T5 model has 2 very interesting characteristics. One concerns the overall training pipeline, namely pre-training and fine-tuning, and the second one is the multitask setting. Now, concerning the pre-training phase, we experimented with 3 different pre-training variations. The first one is the so-called masking objective, in which, given a Java method as input, we randomly mask up to exactly 15% of Java tokens, and then we ask the T5 model to predict this masked token. The second pre-training variations in our study is the following one, is the log position pre-training task, in which from Java method as input, we strip one log statement at a time, that you can see from the left part of the figure, and then we ask the T5 model to guess which was the position of this log statement that we previously stripped away. And in doing so, the T5 model has to inject in the method a specific token, in this case the log statement token. The last pre-training variations that we experimented with features the multitask objective. In this case, what we did was to merge together the first task, the masking task, and the log position task, in this case the second task, and then we train the model on these 2 different tasks at the very same time. Now, concerning the fine-tuning instead, as I told you before, during the fine-tuning we want to specialize the model on the specific downstream task. In our case, we want to support the task of complete log statement generation, and in doing so, from an input instance, again is a Java method, we strip one log statement at a time, and then we ask the T5 model to correctly inject the complete log statement in the Java method. At the end of this process, we have a fully trained T5 model that can support the task of log statement generation by taking as input a Java method having no log statements, and then the output is a Java method with a log statement inject within it. Okay, at this stage of the presentation, let me present you the research questions underpinning our study. So the first one is, to what extent is LACNE able to correctly inject complete logging statements in Java method? And the second one is, how do different pre-training strategies impact the performance of LACNE? And let's have a look at the results that we achieved with the best performing model, that is one featured by the masking pre-training task and the single task fine-tuning, but this one is common to each pre-training variations. Speaking of results, we found out that LACNE correctly predicted the target log level in 66% of cases. Instead, LACNE correctly predicts the position within the Java method of the log statement in 65% of cases. For the log message instead, we found out that LACNE correctly generated the target log message in 16% of cases. Let me clarify here that the accuracy, the correctness of the log message was computed token by token. So, in other words, if token by token the message generated by LACNE is equal to the target one, then we have a correct prediction. And finally, in the most challenging scenario, we found out that LACNE was capable of generating a log statement by picking the correct log level, the correct log message, and also the log position was correct. We found out that LACNE in this case was correct in 15% of cases. But at this point, let me overlap the results that we achieved in the most challenging scenario that we have on the left and the results that we achieved on the log message. Also, keep in mind that we achieved 66% of accuracy concerning the log level, while 65% of accuracy concerning the log position. And given these results, it seems pretty clear that the log message is acting as an upper bound even for the most challenging scenario. And this is kind of positive news if you think about it, because it leaves us a lot of room for improvements. But to investigate further this aspect, what we did was to perform a manual analysis. In this manual analysis, we randomly sampled 300 wrong predictions. Each prediction has a log level and a log position that are correct, but the log message is wrong. Later, two authors manually validated each instance with the goal of finding meaningful log messages that are not the same as the one written by the developers. After that, the third author was involved by taking care of resolving conflicts. After this process, we found out that in 28% of cases, the message recommended by LACNE was still meaningful for developers. And let's have a look at one of these examples. In this case, what we have in orange is the log message predicted by LACNE, while what we have in green is what LACNE was supposed to predict. And if we have a look at these two messages, of course, strictly speaking, we don't have a correct prediction because the token of these two messages are different. But still, what LACNE suggests is meaningful given the context of the try-catch and the context of the method. But besides these cases, we found out cases in which not only what LACNE suggests was meaningful for developer, but even better, because let's have a look at this message right here. It says exception trying to delete subscriptions configuration for subscription ID, while what LACNE was supposed to predict is could not delete subscription for. And if we have a close look at these two messages, it really seems that LACNE was capable of improving the target log message. In other words, the log message manually written by the developer. Okay, so before finishing the presentation, let's have a quick look of what we have seen today. So in this work, I present you LACNE. LACNE is a fully fledged approach that can help developers by supporting them in each logging activities. I explained to you how we train LACNE, and on top of that, also the results that we achieved considering the best performing model. In this regard, the achieved results from the achieved results emerged that in 66% of cases, LACNE correctly predicted the target log level. In 65% of cases, LACNE correctly injected the log statement in the correct position within the method. In 16% of cases instead, LACNE correctly generated the log message. And finally, In 15% of cases, LACNE correctly generate a log statement using the correct log label, the correct log message, and putting the log statement in the correct position. And with that being said, thank you very much for your attention.